Today we are going to start the material of statistical mechanics. Everything that we have worked on so far was thermodynamics. Thermodynamics is a theory of the 19th century when everything is assumed as part of a continuum. All the materials, we don't really know what's going on inside, and we assume that the material is some sort of continuous matter. The interesting thing starts to appear when we look on those phase transitions. Remember this PV curves, right? We have P as a function of V. For example, what we have seen for the van der Waals gas is that there are some sort of jumps, right? We have seen that the isotherms look like this, and then we decided by exploiting the Maxwell construction that there are specific jump from VA to VB, right? And this was a restricted area. Okay, so what do I mean by restricted area? Restricted area means that I don't really know what's going on. My worthless, right? All those curves that are going up and then going down, completely worthless. And I, by the means of Maxwell construction, by simple can only say the following thing, right? That the system reached that point, and if I slightly shift my pressure, it will jump immediately to this point. When I say immediately, it depends on a lot of different factors, right? Because we are talking about only equilibrium states, so we only care about what will happen to the system if we will leave it alone, wait for a while, and then look upon it. But the system in our case is simply jumping from here to there. Now, what actually happens in between? How can we understand this area and how we can exploit it? Why exploitation here is so meaningful? All of the science, like thermodynamics and later on statistical physics and statistical mechanics, was inspired by the heat engine, right? So we're talking about the 19th century, is a little bit after the technological revolution started. It's very, very profitable to build engines, so we need to understand how engines work, how matter is actually operating, and how we can explain it. Okay, so then people started to think, well, yeah, it's a nice story that this is a restricted area, but what actually is going on inside? And in order to answer this question, we need to understand something about not just the macroscopical world, but about the microscopical world. What is matter is actually built from? And today we know that matter built from atoms, and that atoms built from some other stuff, and etc., etc., etc. Thermodynamics does not assume anything, while statistics of V goes to H, right? We can write a Schrödinger equation, solve it, and obtain the microscopical description, quantum mechanical microscopical description. Now, thermodynamics does not know anything about quantum mechanics, etc. And the only thing that we should care about is that in this world of quantum mechanics, we know that there are states, right? We know that when Hamiltonian is applied to some, function, we can write that ni, it's simply the energy of the state, P of ni, multiplied by the state itself. So we know that there are some states, sometimes they are continuous, sometimes there is a discrete spectrum of space, but we know that quantum mechanically our world is described by small states, and the system, sometimes, it just when we measure, we only find it in a very specific set of states. Each time that we measure, we're performing some sort of a measurement, we find the system in a specific state. Right? So this is quantum mechanically. So in quantum mechanics we understand that in order to describe any system, we need to describe it by the means of the states that are present there. Now, what happens in classical physics? So there is, in classical physics, so this is quantum mechanics.
Everything is continuous.
Everything is continuous. There are no states. but we still can describe somehow the states, right? You've seen this before in the class on thermodynamics. So I can say the following thing. I can plot my phase space, right? P is the momentum, and R is my position, okay? And I can discretize somehow specific regions in my state, in my phase space. So this is classical. What kind of an example do I have in mind? So linear oscillator, right? Harmonic oscillator. The energy is P squared divided by 2m plus 1 squared of K R squared. Okay. This is my energy. So for each energy in my phase space, I can plot a contour, right? Okay, so those are contours like isotherms, but this is a contour of a constant energy, right? So for each point on my contour, I can discretize. Oh, sorry, contour. What is a contour? One-dimensional line in 2 dimensions. Okay, so I can discretize and pick a small rectangle, and I would say, well, like here I have a state which is described by some specific eigenfunction. Here I also have a state which is described by specific coordinates of the momentum and the position. Right? Now, why those do you remember why those contours for the oscillators are like somewhat elliptical? Right? So it's like a pendulum. It goes up and down, up and down. So this is the bottom, and then I simply flow to different states. Yeah, yeah, exactly. If you remember, energy is P squared and R squared. Okay, so eventually this constant E. So this is an equation of an ellipse. Right, and what's going on? The flow as I'm crossing from one state to another as a function of time is simply I'm staying at the same contour on the same contour all the time. I'm just moving along it. You've seen this in analytical mechanics several times probably. So the point is that I can describe states for quantum mechanics. I can describe states in classical system. The problem with this description, there are huge amount of states, right? So we know how to solve very specific examples in quantum mechanics, which are more or less this oscillator plus maybe an hydrogen atom and maybe some other examples. So there is not a lot of them, of the examples that we can actually solve. The same goes for classical physics, right? We can solve a small number of real physical systems, more or less this oscillator, right? And some modification to it. And for any real system, the number of states or the complexity of this phase space, which is becoming many-dimensional and not just simply two-dimensional, is extremely complex task. Right? So I cannot simply say, well, I want to study statistical mechanics. This means that I need to solve all my problems by solving some quantum mechanical equation or solve some classical physics equation. I simply cannot achieve those tasks. So in order to continue, I do need to take into account that there are states, right? But I also must admit that I cannot really fully solve any physical problem. Right? I need to assume something about the behavior of the system, about how the different states look like. But I cannot start solving whatever is going on inside by simply saying, let's solve this gas. Exactly. We cannot do this. So the advantage of statistical mechanics is that, yes, it assumes something about the microstates, it assumes something about the microscopic description, but it's not going as far as to solve the Schrödinger equation or Newton equations in multidimensional systems. No. It simply uses this notion, in order to describe something microscopically, I need to know that there are different states. Okay? So this is our initial assumption in statistical mechanics. We can, no. We can reach any state. The assumption is that we can reach any state. The question is, can we show exactly what is our function, eigenfunction for this state? I don't know. Right? How many, you have already had class on quantum mechanics. How many problems have you solved? Exactly solvable problems. 2? 3?
Problems.
3 problems?
Yeah.
Hydrogen atom, oscillator, and what else? Okay, yeah, that's it. Okay, so particle in a box. Right, that's it, right? Yes?
Well, we can solve many more problems. If we look at those problems as like these problems plus.
This is a good idea. So we can approximate something by using those problems. You're completely right. But if I'll tell you, okay, so what are the eigenfunctions of this marker? Can you solve it? No. Nobody can, right? And there is no even a computer that can solve all these problems. Okay, I cannot even simulate the quantum mechanical behavior of this marker. I'm doomed, right? So I need to use assumptions. Yeah, so this is what we're going to do in the quiz. Solve the quantum mechanical problem of this. Now, so where I'm trying to get you? I'm trying to get you that my understanding of statistical mechanics is if I'm thinking about different bricks as states of the system. So I have A, B, C, D, F, G, and whatever alphabet letters that I have, right? All those different cubes, or whatever, are different states of my system, right? And my description or my understanding of how this system behaves as a function of time, I assume that the system is continuously going from one state to another, okay? And there is a trajectory in the state space. Okay? I don't really know how exactly this trajectory looks like, but I know that the system is going from one state to the second state, to the third state, to the fourth state, etc., etc., etc.
Each state is just some set of...
So you can assume that each state is a quantum mechanical state, full quantum mechanical states of all your parameters, or it's a specific point in the phase space over here. Okay? Like for example, in this oscillator, I'm going from one rectangle to another. So each of those are my states, right?
It's for the whole system or just one particle?
It's for the whole system. Okay, so here the whole system is just one particle. But this guy has many states, and it's continuously going from one state to another. Sometimes it stays for a while in a specific state, etc., etc. Okay?
In thermodynamics, we also assume that the system has states.
Have I ever used the word state? State is described by small amount of parameters, like extensive variables, or intensive, but there was like 5 of them. Here, the state is described like this quantum mechanical eigenfunction, by the whole position of all the particles in the system, by everything. Okay, so if I have this amount of gas, I have 10 to the 23 number of different parameters that describe my state. So in theory, or even in experiment, if we measure energy, up to now, we assume that energy was something constant, right? We use the word E. But in practice, if you look on any phase system as a function of time, any real system, not highly constrained, what we see that the energy as a function of time is actually following this logic over here. The system is jumping from one state to another, and the energy is also jumping from one state to another. In any real physical system.
So you pass discontinuously between the states?
Sometimes it would be perform discontinuous jumps. Sometimes the states are so closely positioned on this spectrum, you basically see almost continuous jumps. Right? It depends on the spectrum. If my spectrum of the states is discrete, I will observe discrete jumps. If my spectrum is continuous, I will observe continuous transitions. If my measurement equipment is not delicate enough, right, and I don't see those jumps, or they are extremely small, I still will see some continuous jumps, right, continuous behavior. So what is the energy that we used so far in thermodynamics.
The energy of the entire system.
But this is the energy of the entire system, and this is the energy of the entire system, and this is the energy.
Average.
The average. Okay? So what he has used so far is that we cross a line over here. Okay? We call it E bar. Let's call it U. Okay? This is the average energy of the system. When you're thinking about any system and that it jumps from one state to another, the energy also can jump from one value to another. So the energy is constantly changing. Right? There is an exchange energy between myself and the whole environment over here. So I cannot simply say what is the energy. I can answer that the energy, that there is an average. Right? So what we have used so far in thermodynamics is the average value.
But it's not the average over time, it's the average over the particles.
What? Why?
That's
What do I measure in experiment? How I perform in my experiment. So eventually, everything has to be defined closely by whatever the experimentalist tells me. So I'm going to the lab and I'm asking what is the average energy? What the experimentalist will perform? The average over time. He will look on the system and we say, well, here it was in position E1, right? Here it was in position E2. Here it was in position E3, okay? And etc., etc., etc. Okay? I will record all the different outcomes, all the different positions, all the different values recorded for the energy. Okay? And E is going to be this guy divided by the number of sampling points. So 1 over n. This is averaging over time. The index 1, 2, 3, 4, 5 means the measurement, the time. Okay? Yes. היא פשוט עוברת עם הסביבה. Oh, sorry. The energy, but it's recorded. But it's recorded.
It'll be grave consequences.
But it's still recorded. No, it's recorded. So the energy, any system can exchange energy with its environment. So if the energy is closed, okay, so it's going to be exactly the same energy anytime I measure it. You're right. But if it's can exchange energy with the environment, it's going to change a little bit. We are trying to talk about real life systems. Yes.
Can you still assume that the variance in energy is much smaller than mean energy?
Sometimes yes, sometimes no. It depends on the system. Okay. But this is the averaging. So this is a little bit of a problem. Why is it a problem? Why it's a problem? Because I want to compute something, right? I don't want to go each time that I'm thinking about a system. I don't want to go to the lab. I'm a theoretician. I hate labs, right? I hated them from my first year in university. I hate labs. I want to compute something. What do? Right? So I need to measure. This is what it tells me. I need to go to the lab and measure. So I'm a little bit doomed, right? But not all hope is lost. So this is great, but this is not what we want. We want a tool in order to actually measure averages. This is a bar. This is simply 1. This is 1. This is simply 1. So what do I do instead of that? I'm saying the following thing. So we can take this right hand side and we write it down as what? Okay. So we sample instead of all the different measured positions. I will do the following. I will measure over nu. This is the index. All possible values of energy.
This is what we do when we measure energy.
This is what we do when we measure energy.
Okay.
This is what I want to do. Right? All possible values of energy. So this is E nu, right? But you see, it's this sum definitely does not equal to this sum, right? First of all, there is no 1 over n. So I'll introduce here 1 over n. Okay? And here I will count number of times state nu was visited. Okay? So I'm counting now a little bit different. Instead of just simply saying E1, E2, E3, I'm saying, look, I'm looking, this is my state, right? So this is E nu. What I'm going to perform over the whole time n, I'm going to measure the number of times that I visited in this vicinity of E nu. So here once, here 2 times, here maybe a third time. Okay? So instead of doing that, right, I simply resum everything. So I have 1 over n, number of times state nu was visited.
But you still need to wait a long time.
Yeah, I need to, I completely agree with you. I need to wait a long time in order, but this is exactly equals to E bar. Okay? Haven't made any assumptions yet. I just resummed everything here. Now, what do you remember from statistics class about the number of times? Number of times state. Oh, exactly. It was visited. Divided by n, and the limit of n goes to infinity. What is this? Okay, you studied this. No. The law of big numbers, large numbers, right? So this is exactly the probability. This is exactly the probability. You're completely right. This is the probability of P nu. The probability, okay? The probability of being in state nu. Okay? This is the law of large numbers, right? This is absolutely provable with some assumptions in the statistics class, and whoever was in my class have proven this, right? Hello. Okay. Now, whoever have studied in the mathematics department probably knows about a lot of sigma algebras, but not about probability. Sorry about that. This was exactly the case with me. I studied probability in the math department, knew a lot about sigma algebras and different space properties, but nothing practical. So what we have over here? Look, so this guy goes to, under this assumption, okay, to the sum over all the different states, P of ni, right? The probability to be in state ni, E ni. Okay. What is this? This is called, no, not E bar. Tochelet, right? The average. This is the average over distribution. E bar was the average over time. This is something that I go and measure in experiment. This is something that I can go and write down in my notebook as long as I know the different probabilities and actually calculate. This is the theoretical. This is called disorder average. Disorder average. ממוצע על disorder. ממוצע לסדר. Okay, so this is ממוצע הזמן, time average. This is disorder average. And the basic assumption of statistical mechanics, this is called an ergodicity hypothesis, that E bar. This means that if I have a time average and it equals to the ensemble average, ensemble average. Ensemble average. Okay. So ensemble average and time average, they're equal to each other. This means that I can calculate stuff. I don't have to only measure them. Okay? I only need a model. In this model, I need to obtain what are the different energies or other observables. I need to calculate the probabilities of being in specific states of my system, and then I compute all the averages. Now, this ergodicity hypothesis is not only for energy. If I have any observable, right, I can say, what is P bar? So I want to calculate the average pressure, right? I can measure it as a function of time, or, right, I can calculate it in theory. And this goes for any observable O. The volume, the energy, the magnetic flux, whatever. The ergodicity hypothesis simply tells me that if you want to calculate something that you actually observing in experiment, you go and you calculate the ensemble average of this guy. O bar. What is O? Brackets is sum over ni, P ni, O ni. That's it. Right? So for any model, what I need to assume, what I need to obtain is what are the different states of the system, what are the probabilities of being in different states, and what are the values of my observable in those states. The energy is very simple, right? Yes?
Aren't we assuming linearity when there aren't necessarily ones?
Well, in what sense?
Expectations.
Sometimes states are dependent on each other.
Expectation is linear.
So expectation is linear, but this is a hypothesis. Right? There are systems where this is not working. I like to mention glasses, like exotic systems. So there is no ergodicity hypothesis in glasses and many other systems. Most of the systems this holds, and it's based on linearity of expectation value. But you assume this. You basically assume this. Okay? Yes?
In the time average energy, why are we dividing by all the possibilities?
By n? Because it was in the original formula.
Why it's not the total time of the measurement?
So n is the total time of my measurement.
Alright,
Okay?
thanks.
My measurements are discrete, so I'm saying that I'm measuring every second. Yes?
איך אתה יכול להגיד שמשהו שצריך לעשות לו גבול שווה למשהו שהוא כבר...
This is my assumption. This is why it's called hypothesis. I hypothesize this.
זאת אומרת, אני מניח שהסברה שלך היא בעצם קבועה?
No, I simply say that this guy equals to that guy. Right? And there are specific terms why it can happen. Okay. So this is more fancy wording. We will usually, I forgot, we will usually use this term ensemble average. Okay. Whoever is reading papers about specific averages in physics, usually the term disorder average is used, but we are going to use ensemble average. So my bad. Yes.
למה התייחסנו גם ל-P וגם ל-O?
So for any observable, this hypothesis holds.
אוקיי, זאת אומרת, גודל שהתקבל.
That's it. All right. Okay, but what I have told you so far, so great, we have ergodic hypothesis, and we want to measure some specific observable, right? This observable is O, and I'm simply saying this is ni, P of ni, O of ni, right? And before, like 5 minutes, 10 minutes ago, I told you it's impossible to solve any physical problem, right? You have solved 3 problems in quantum mechanics. You have solved 10 problems in analytical mechanics, right? Most of them somehow related to oscillators or very simple systems. How can I obtain all the different states in my system, right? Or how can I calculate all the different probabilities? I have told you that it's impossible. I have told you that this is impossible. So what do? All statistical mechanics is based on assumptions regarding P of mu. I assume what are my different probabilities are. It's like guessing, right? So this whole field of statistical mechanics is based on general assumptions. What are my phase space? What are the different probabilities? The observables, well, I can actually usually work around these observables. How can I do it? I mean, usually in order to obtain some information, so I have assumptions regarding P mu, and I have simple models to describe O nu. I cannot solve real problems, but I can build up simple models in order to mimic the true behavior of any physical system, right? And I assume that I can learn something from my simple models. And it actually works, right? So I completely say I'm incapable of doing everything. I'm incapable of solving everything, but I do capable of making clever assumptions, and somehow all those clever assumptions work. And those assumptions work because we are using or we're looking on statistical properties. And in statistics in statistics sometimes a lot of details are unimportant. Like the law of central limit theorem, right? You have studied. In the central limit theorem, the only thing that I care about are two parameters, and that's it. So this is why in statistics, in a lot of cases, I can make clever assumptions about my different distributions. I can make some assumptions about how those different states appear by using simple models, and that's it. So what we are going to do now, we're going to describe where the hell those P nias are coming from. We use different ensembles to describe them, and we use simple models in order to describe those observables, O nu. So the first part is extremely simple. It's called microcanonical ensemble. Okay. Microcanonical ensemble. So in physical terms, what I assume the E equals constant. And the system is closed. Right? So I do not have exchange of energy with the outside world. The number of particles is kept constant. The pressure is kept constant. Everything what I can think about it kept constant. Now, it's still not clear from those assumptions what this difference P nu should be. And here I'm going back to statistical class, to the class of statistics, and I ask you, so we had a sample space, מרחב מדגם. And this sample space included different outcomes of the experiment. We can assume that those different outcomes of the experiments are the states of my system, right? I measure, I see trajectory of my system. So each point in on my sample space, think about it like the Venn diagram, right, is the state of the system. What was the first example and maybe the simplest example of the probability law that you have been given in your statistics class? Uniform. This is the simplest one. Right? When you are taught about probability, this starts with flipping a coin, and I assume that the probabilities of the heads and the tails is exactly the same, 1/2, right? We assume something about the probabilities, and the most basic assumption is the probability of uniform distribution. Microcanonical ensemble, this is exactly what it is. We assume that we have different states in the system. We assume that for each state, there is exactly the same energy, it's because it's constant, and we assume that the probability is uniform. This is our assumption. Will it work? Well, we can build a model and we can afterwards test it in an experiment and see how it works. But this is assumption. Why I have to assume this? Again, because I cannot solve anything properly. Okay? So I'm assuming. Now, so all the different states that I have in my system, they have exactly the same energy. And my goal is now for the microcanonical ensemble is to use this information over here, constant energy, constant everything, okay? And use this probability as uniform somehow to get into explanation of okay, what I'm doing actually. How I can obtain what is the temperature of the system, right? What is the entropy, what is the pressure inside the system. We used in thermodynamics many physical, not many, some amount of physical variables, extensive variables or intensive variables. How I'm going from this statistical description to the description in terms of state functions, right? Like for example, for the ideal gas I have PV and RT, right? This is a state function that it somehow connects my pressure to my volume to my temperature. How I'm obtaining equations like that from this description? I need a tool. Okay? And my tool is entropy. Okay? My tool is entropy. How I define entropy. So far I haven't told you anything about entropy. I just said something about that it's a growing function of energy. It's under a second law, and if a process is adiabatic, the entropy grows. It has to be maximal with respect to constraints, etc., etc., etc. What is entropy? How is entropy is related to the number of states? Oh, you know. Why it's KB1? Let's call it omega. Okay, so think about it in the following. So we will later prove everything exactly, and when we define something that is called Shannon entropy. But for now, think about it. If I have a dice, right? So I'm throwing the dice. The number of outcomes is the number of states in my system, right? My system is a dice. The measurement mechanism, I throw the dice and look what number I'm getting. I can get 1, 2, 3, 4, 5, 6. So there are 6 different states in my system, right? Okay. If I have 2 dices. So this is one particle system, and it has 6 different states. If I have 2 dices, right? And I throw 2 dices at the same time, how many states do I have now? 36. Okay, so the number of states in the system is multiplicative function of number of particles. But the entropy is a linear function of number of particles. Right? So I cannot simply say that my entropy is the number of particles that I have in my system. Right? I'm using the following assumption, that is, in order to get something out of multiplicative function, what I do, I take a log of this function and it becomes linear. Okay? So if I have e to the power of n, log of e to the power of n is n log e. Right? So in order to get a linear function of number of particles, I take a ln of omega, I multiply it by a specific scale, let's call it k Boltzmann, okay? And this is s. So this is how I define the entropy, and I will prove it more generally for any ensemble later. But for microcanonical ensemble, the entropy is just log of the number of states multiplied by k Boltzmann. Okay, what is k Boltzmann? With Boltzmann constant. Okay, and what are the units? Joule divided by Kelvin. Okay, so this is a Boltzmann is 1.38, right? 1.38, yes. Multiplied by 10 to the minus 23 joule by Kelvin. All right, so now we have a tool. We can have our entropy, okay? And the moment that we have entropy, we can do all different stuff, right? Because you remember, if I have entropy and I take ds to du, okay, equals 1 over t. So if I know how to compute the number of states in my system, I assume that the probability of each state is uniform, okay? And I want to obtain some sort of a state equations like this guy for thermodynamics. I take S, I write it down in terms of the energy of my system or the average energy of my system. I take the derivative and I relate it to the temperature. And that's it. And then I can play all these different games of thermodynamics. In order to actually finalize something, we still need to use a specific model. Okay? Unlike thermodynamics, where everything is global and universal, but very amorphous and not clear what exactly I have to do, in statistical mechanics, it's very simple. You have assumptions about the probabilities, and you have a very specific model. You cannot do stuff very generally. You need a specific model in order to work on it, in order to compute the energy, in order to take derivatives. So you always start with a specific model. Okay, so our model is going to be the Einstein model for solids. No, this is what we are going to use later. This is the tool. We are going to compute S, and we're going to take a derivative of S with respect to entropy and energy, and this is going to be our starting equation. You will see it in a second in the model. So, the Einstein. This is an example of how you operate with microcanonical ensemble. Okay? The Einstein model for solids. So it goes back to 1907. So the assumption of Einstein goes like this. We have a solid, and inside a solid there are atoms, or some particles. And the particles are extremely complex, and they somehow affect each other. Maybe, maybe not. They have properties, and you can apply pressure on them, and you can heat them up, you can cool them down, etc., etc., etc. So what was the cleverest idea that Einstein, so this is a three-dimensional stuff. Okay. What is the great idea that Einstein, he looked on this, he thought about solids, and he had an idea in mind of how to describe a solid. So what you would do in the place of Einstein. Everything extremely complex. When everything extremely complex, what do you assume as a physicist?
Harmonic oscillators?
Harmonic oscillators. So everything here is harmonic oscillator. And it can oscillate in 3 dimensions. Each particle is an harmonic oscillator.
In a specific direction, right?
So x, y, and z can oscillate in the x, it can oscillate in y, it can oscillate in the z. What are the different interactions between the different atoms? None, right? This is the simplest assumption. In physics, you try to be as simple as possible, hoping that it still will get you somewhere. Okay? So we know how to solve eventually stuff about about harmonic oscillators, and we know how to solve problems where there are no interactions. Because the moment that there are interactions, we don't know to do anything almost. Right? We can solve 2-body problems, we sometimes can solve 3-body problems. Here we have 3n degrees of freedom. Right? and n can be as large as Avogadro number. Okay, so we cannot solve actually anything. We have to assume something. So those assumptions of Einstein. We have 3n degrees of freedom, 3n harmonic oscillators. Harmonic or independent harmonic oscillators. Great. Now we all can be Einsteins. Okay. Now, of course, we know how a harmonic oscillator looks like if we look on the energies. So En is h bar omega 0 multiplied by n plus 1/2 h bar omega 0. Right? The other way, no, this is good, right? So Einstein wasn't aware of the quantum mechanical. What? Right. But Einstein wasn't aware, but he already knew something about this stuff of quantum, right? From his paper from 1905.
Who
So
didn't believe in it?
everybody believed in it immediately. So this is 1907. He already really famous, right? So for example, his paper on Brownian motion. So it was a prediction about how Brownian particles are moving inside liquids. This got the Nobel Prize, not for him, but for the guy who took his theory and performed the experiment, Jean Perrin, right? So Einstein already famous. Maybe he haven't got his Nobel Prize yet, but he's already really famous. So people do believe him, or at least the theory looks fine. Now, you don't really care about this guy over here, right? You don't really care. It's about, well, where you start counting your energy. And Einstein haven't really solved anything quantum mechanically. He assumed about specific quantum of energy that each particle or each degree of freedom can actually obtain. So there is nothing like this over here. And n goes 0, 1, 2, and 7.
רגע, מה נמחק משם?
We don't, so if you think about the energy scale, right? This term only tells you where you put your 0. That's it. You can always start to count from this baseline, and that's it. Yeah. So it's not that Einstein thought about the harmonic oscillator quantum operator and solve it like you did in the class on quantum mechanics. No, he had this assumption about how light is actually penetrating systems, so there should be specific oscillations, and those specific oscillations contribute to what? To specific energies. That's his assumption was. Now this is interesting because, you know, afterwards all this discussion about quantum mechanics and the dispute with Niels Bohr, etc., but he already uses those quantum mechanical assumptions in almost everything that he does. About not relativity, his other babies, but about soft matter or hard condensed matter, etc. Alright, so great, so this is the model. This is the Einstein model of solids. Extremely simple. We just oscillate in a second. And each oscillator, we have 3n of them. They do not interact. Each of them can have these levels of energy. Yes?
למה זה אוסילטור חד-מימדי מה שרשמת, האנרגיות, ולמה לא תלת-מימדי?
Okay, so if the question is, this is one-dimensional, not a three-dimensional, I assume that there are 3n of them, and each of them is independent of the other. So when my oscillator is oscillating in the x direction, it doesn't care, it also can oscillate at the same time in the y direction. Right? It's a separable problem. It's a separable problem. Right? So this is an assumption that we have 3n degrees of freedom, and each degree of freedom is having those energies, or those states. Okay? Great. So how do we need to count, in order to proceed and actually compute something, we need to count the number of states. So how we go from here? The procedure, the solution. Yes.
אני מבין את העניין הזה שהוא ניסה לפשט את זה לצורה חדשנית שזה כל אוסלטור בעצמו, אבל ברמה הטכנית זה הכל כאילו מצומד, כל העניינים.
You're right. This is why this problem eventually fails. But it works extremely well for high temperatures, And we will understand later why. And for lower temperatures, it fails. So he had something in hand which works, at least at the temperatures that are high enough. Okay? And the idea is, this is what we see later, that at high temperatures, those interactions are not important. Yep, exactly. Now, we will repeat this procedure again and again in this class, and this is what you always do in physics. Eventually, we can solve non-interacting systems. That is what we can solve. And every solution of any physical system is eventually a solution of non-interacting system. But what we will manage to perform is to describe the system somehow differently. Remember, the only thing that nowadays we can solve is non-interacting systems. How we do solve interacting systems? We somehow describe them or disguise them such that they look to us as a non-interacting system. Einstein simply assumed, well, I will start from non-interacting system and we'll see what we're getting. Okay, so what we're doing in our solution. Number one, we count the number of states. The number of states.
How do we do that?
We will see this in a second. Number two, we compute number of states, which is equals omega. 2, we compute S equals KB log of omega. Okay. Number 3, we write down 1 over T equals to ds to du. Okay. This is the whole solution. The problem, of course, is this. So it's not that everything is very simple. We have here some sort of a combinatorial problem. Okay, so this is a microcanonical ensemble. So the total energy equals U. Okay. Now, how many quantas? So if U is total energy, some of the quantas of energies are in oscillator number 1. Some of them in oscillator number 2. Some of them in oscillator number 3. Some of them in oscillator number 4. Okay. So the number of states is actually to count all the different configurations of all the different oscillators. Right? So I have this guy, U divided by H over omega. This is the number of quantas of energy distributed among 3n oscillators. Okay. And the number of states is how I can distribute U divided by H bar omega into 3n different boxes. Think about each oscillator as a box. It can have 1 quanta, 0 quantas of energy, 1 quanta of energy, 2 quanta of energy. In total, I have U divided by H bar omega. Okay? And I somehow need to mix them up in all the different boxes. And the number of combinations that I can shift my different quantas of energy, the number of combinations is exactly the number of states. A state is a specific distribution. The number of combinations of those distributions is the number of states in my system. Now, think about different energies as specific circles. Okay, so I just line them up, all the different, so how many circles I have? U divided by H bar omega, the number of circles. This is the number of quantas of energy. Okay, I need to put them in 3n boxes, right? How I describe it? So I put lines over here. How many lines? How I need to have 3n boxes, right? How many lines I have to plot in order to 3n minus 1. Okay, so I have u h bar omega number of circles, and I have 3n minus 1 number of lines. How many objects in total do I have? So the number total of objects, I have u divided by h bar omega 0 plus 3n minus 1. In how many ways I can recombine all those different objects?
U חלקי שומגה 0 ועוד 3 פחות 1 ועוד 1 מעל...
u h bar 0 minus plus 3n minus 1. Factorial. This is the number of ways that I can basically reshift all the different objects. I assume that I have the sum of quantas, so this is the circles, plus the lines. Right? But I don't care what I don't care about the order of the circles, right? And I don't care about the order of the lines. So I have to divide it by 3n minus 1 factorial and u divided by h bar omega 0 factorial.
Binomial.
Like a binomial, right? But this is two boxes. Like a binomial, exactly. But it's the proof is slightly different than just a binomial. Okay. So this is omega. This is the number of states. Number of states in Einstein solid. Okay, so I solved the combinatorial problem, and now I know what is the number of states. Okay. The next step is to compute S equals KB log of omega. Okay, so what is logarithm of factorial? So you know. We are going to use a Stirling approximation, right? Stirling approximation. What is a Stirling approximation? N factorial, okay, log n factorial equals n log n minus n. When it works,
אין גדול מ-1 ל-3.
and log very large.
לא very large.
Okay, so usually what you have been, so what I was told is that n has to be very large. But when you go and check, there are some small additions. You go and check, around 2 it works pretty good. So 2 is a large number. Okay. Yeah. All right. So this is what we are going to do. We are going to take a log of this guy. Okay, and we're going to sweat a little bit. Where I'm getting into, I want to make this formula a little bit nicer, such that when I take the derivative, it's going to be nice, right? So I don't want to leave all those factorials inside. They're pretty ugly. Okay. So we are taking log of u divided by h bar plus 3n minus 1 factorial divided by 3n minus 1 factorial u divided by h bar omega 0 factorial. This guy equals to log of u h bar omega 0 plus 3n minus 1 factorial minus log of what we have here, 3n minus 1 factorial minus log of u divided by h bar omega 0 factorial. Now we have this Stirling approximation. Okay, so we are going to have here 3n minus 1 plus u divided by h bar omega 0 multiplied by log of 3n minus 1 plus u divided by h bar omega 0 minus 3n minus 1 plus u divided by h bar omega 0. Excellent. Minus 3n minus 1 log of 3n minus 1 plus 3n minus 1 minus u divided by h bar omega 0 ln of u divided by h bar omega 0 plus u divided by h bar omega 0. Okay, so what do we do now? We take this guy and separate it into the following multiplication. So what we have here, we can have this guy. So I'm taking the 3n minus 1 multiplied by the log, and I write the log as a multiplication. So I have 3n minus 1 multiplied by a log of 3n minus 1 plus a log of 1 plus 1 over 3n minus 1 u divided by h bar omega 0. Okay, so this is this term multiplied by this term, and I still have this term multiplied by that term. So plus u divided by h bar omega 0, a log of, now I separate this value, and you see I here have log of u divided by h bar omega 0, and here I took out the 3n minus 1. Now I'm taking u divided by h bar omega 0. So ln of u divided h bar omega 0 plus log of 1 plus 1 over u divided by h bar omega 0, 1 over 3n minus 1. Fine with everything? Hopefully. So this is this guy. Okay. What else do we have? We have minus 3n minus 1. We have minus u divided by h bar omega 0. And we have this line. So we have here minus 3n minus 1 log of 3n minus 1 plus 3n minus 1 minus u divided by h bar omega 0 ln of u divided by h bar omega 0 plus u divided by h bar omega 0. And now it's the time for the red marker. Yeah. Okay. So what we are losing? So this guy goes with that guy, right? And this guy kills this guy. What else? Look, here have 3n minus 1 multiplied by log of 3n minus 1. Okay, this term, and we have minus. So this guy kills that guy. Okay. And what else? U divided by h bar omega 0, ln of u divided by h bar omega 0. Here we have u of h bar divided by omega 0, ln of u divided by h bar omega 0. Okay, this is it. So we have this multiplied by this, and this, what I have, and this multiplied by that. Pretty straightforward so far, right? Yeah, you.
Well, at least straightforward part was the beginning. We just split up.
Okay. Okay, so what this was? So this is log of what? This is log of the number of states, right? What is log of number of states equals to? No. S divided by K Boltzmann. Okay? So we can now write down the simplified expression for S. So S is K Boltzmann, and here we have 3n minus 1 multiplied by log of 1 plus 3n minus 1 divided by u h bar omega 0 plus u h bar omega 0, so plus K Boltzmann u divided by h bar omega 0 log of 1 plus u divided by h bar omega 0 multiplied by 1 over 3n minus 1. Very nice, extremely nice. Now, this is, so we have, yes?
The other way around, it's minus 1 plus 1 plus u over
Where I made the mistake?
You just need to switch between the lines.
I need to switch between the lands. Right? Ah, so this. Alright, yep, thanks. Okay, so here I have u h bar omega 0, 1 over 3n minus 1. And here I have 3n minus 1 divided, divided by u by h bar omega 0. Okay, thanks. The final step, 1 over t equals to ds to du. Okay, so let's take the derivative of this guy. Yeah, great, right? So 1 over t equals to, this stays the same, so this is k Boltzmann, 3n minus 1. Okay, and here I have a derivative of this guy. So this is multiplied by 1 over 1 plus 1 over 3n minus 1 u divided by h bar omega 0 multiplied by what? 1 over 3n minus 1 h bar omega 0. So this is the derivative of this guy. Okay, so now we're taking the derivative of the second part. The first is simple. So this is plus k Boltzmann h bar omega 0 log of 1 plus 3n minus 1 divided by u divided by h bar omega 0. Okay? And then the derivative of the log. So plus k Boltzmann u h bar omega 0 multiplied by 1 over 1 plus 3n minus 1 divided by u divided by h bar omega 0. And the last part is what? The derivative of this guy. Okay, so it is minus, right? 3n minus 1 divided by u squared h bar omega 0. Seems okay.
How do you check your intuition at this point?
I'm completely dependent on you guys to saying, well, Stas, you have missed something here or something there.
Stas, is this
Where
supposed to
is
be
it
a
you?
Use the derivative calculator for that.
No. Use your brain. What?
supposed to be a U
Before the first
before-
line.
This is you.
No, before.
This is what?
Before the line,
Before the
KB.
line.
I took a derivative with respect to you, so this disappeared. This was a u over here. And I took a derivative.
Ah,
Okay? Wait.
ah.
Don't worry, eventually we will get something very nice. And feel completely unsatisfied.
How did Einstein know about the energy levels of those things?
He assumed stuff. He was Einstein.
Magic.
Yeah.
הנה סטס, מצאנו לך טעות.
Where?
היו בריבוע, צריך לשים שם חלקי H bar.
So there, okay, this, so it's upstairs, right?
כן.
Okay, so this is here. Thanks. H bar omega 0.
אפשר לצמצם.
Okay, yeah. Okay, so what we are getting to? You want the final solution, or you want to wait that me to struggle a little bit here? Okay, so yeah. So look, it's actually very simple, right? So this guy goes with this guy, and we took the h bar omega over here, and here, for example, u squared is disappeared with the U over here, okay, and etc. etc. So there is a lot of disappearances that happens, okay, and after I took everything into account, I reached the following extremely simple line, which A bar divided by K boson T equals to log of 1 plus 3n h bar omega 0 divided by U, 3n minus 1. This is it. Yeah. Okay. This is as simple as that. All right. Let's take an exponent over everything. Okay. Of the left-hand side and the right-hand side. So we're getting E h bar omega 0 by K boson T equals 1 plus 3n h bar omega 0 divided by U. Okay, where I assume that 3n minus 1 is approximately 3n. Right, in the large limit of n is extremely large, so 3n minus 1 is something like 3n. Okay, so let's take this to the other side. So we are getting e to the h bar omega 0 divided by K Boltzmann T minus 1 equals to 3n h bar omega 0 divided by U. Okay, so
It's supposed to be 3n minus 1.
yeah, I'm telling that 3n minus 1 is approximately 3n. Large, the limit of large n. Okay. So we are getting that U equals to 3n h bar omega 0 multiplied by 1 over e to the h bar omega 0 divided by K Boltzmann T minus 1. Okay. Or, write it over here, U divided by 3n equals to h bar omega 0 multiplied by e h bar omega 0 divided by K Boltzmann T minus 1. What is U divided by 3n? So this is the equation. That's it. We are done. All right. So pretty nice. Now what is this? What is U? So the energy per particle or per oscillator. Okay. So per oscillator per degree of freedom. And what do we see? So it's simply h bar omega 0. Right. It's like the first excited state, right? Multiplied by some specific prefactor. Exactly. So we're getting to the partition function. We will meet a lot. You already seen them. You already seen this expression, e to some energy, because h bar omega is 0. H bar omega 0 by K Boltzmann T. You've seen this a lot, and you will see it even more in this class. So this is related to some partition function somehow, multiplied by h bar omega 0. Okay, so this is energy. This is unitless prefactor, and that's it. Okay, so you work a lot, but eventually it's kind of satisfying because you assume that there are no interaction, and this is exactly what you're getting. Now, you want to calculate some other stuff. You want to calculate the specific heat capacity. Okay, come on, take a derivative, take an integral, or whatever. So all the tools that we slightly mentioned, but you have learned in the class on thermodynamics, all the tools are applicable to this equation. You have everything. You have the energy, you have the temperature, you have specific parameters of the system like h bar or omega 0. You can calculate whatever you like or whatever you want. Okay? And the problem with this is, does it work? And the answer is, it actually works pretty well when the temperature is high enough. We'll see it when you deal with canonical ensemble, but when the temperature is good, high enough, okay, this description of the system with the energy and etc. works pretty well, actually pretty well. Now, so the whole problem was here what? A combinatorial problem. If beforehand we had no intuition, now we do have some sort of intuition. The only thing is technical problem. Okay? The microcanonical ensemble. We need to push the energy into different boxes. This was the most complex state. Not all of this. This is algebra and some techniques. The thing was I had a lot of different energies or quantum energies. How I distribute them. How I compute the number of states. This is the difficult part. Everything else was some algebra, and you can solve it nowadays with Wolfram or whatever. Actually, really simple. Okay? But the combinatorial problem can be sometimes extremely hard. So we have another 10 minutes. So I will show you another example. Right? So this was the Einstein model, and we will continue the Einstein model when we will treat the canonical ensemble. I won't start the canonical ensemble. Instead of, I will solve another problem for microcanonical ensemble. Yeah. What? T goes to infinity. So room temperatures are high enough, usually. Room temperatures are high enough, yes. So not superconducting temperatures, but let's assume boiling temperature, as long as we still have solid.
זה לא תלוי בטגע, זה לא צריך להיות ש-K ביטים גדול מ-H באומגה 0?
No, you don't really know. You don't really know what it is. So it's some sort of a parameter for you. We will see.
Because
What? Yes.
we can't see the interaction very well.
Exactly.
When it's cold.
Exactly. So what we have, the question is why it's not working for low temperatures. I'm telling you, it's working good for large temperatures or high temperatures. Why it's not working for low temperatures? It's not working for low temperatures because we neglected any interaction, right? Not we, Einstein. Okay? We neglected any interaction, any possible interaction in the system. So in 1912, a guy named Debye came along and said, well, I can correct the Einstein method, and we will see how to do it. Beforehand, let's solve another example. Two-state model. Okay. Again, we need something simple, otherwise this combinatorial problem, okay, in all the models, in microcanonical ensemble, you assume that you have a constant energy, and then you have to, in some way, to shift this energy between different states. Right? This is how you compute the number of states in the system. So it usually involves extremely complex combinatorics that only in a quiz you can solve. Okay? It's a joke. It's a joke. Okay, so, but usually it involves complex combinatorics, so we only treat simple models, really simple models. So a two-state model is saying the following. And number of particles in the system. Okay. All the particles are non-interacting. Non-interacting with each other. Okay? Each particle can either have energy epsilon or 0. That's it. So we have n particles. Each particle is a two-level system. Okay. In quantum mechanics you have two-level systems. In optics you have two-level systems. Here we also will solve a two-level system. So for each particle, if you look on the spectrum, it has 0 energy and epsilon energy. And that's it. Now we assume that the total energy equals U. Now we want to obtain some sort of a state equation. Again, like before, we obtained that there is a connection between energy and temperature. Something like this, we should obtain over here, right? Use a function of T. Because the moment that we have an expression for the temperature, for the energy, okay, we can do whatever we like. We are absolutely good derivative. We are perfectly fine with the thermodynamical laws, and we can compute everything. We don't really care. So our goal is to obtain a connection between the energy and the temperature. So what do?
We say that U is M multiplied by epsilon.
So we go in the same spirit as we do in the Einstein model. So here we have a quantas of energy. Okay. So the total number of quantas of energy in the system is U divided by epsilon. Of energy in the system. How many boxes do we have? N atoms we have, okay? So I'm saying the following thing. We have the total number of atoms, okay? Or the total number that for each atom now we can push one piece of energy. Each atom now obtains, or each particle here is obtained either 0 or epsilon. Okay? So we need to distribute U epsilon of energies or quantums of energies into n different particles. So it's like choosing U over epsilon particles out of the box that contains what? N different particles. Okay? So this is the binomial coefficient. Right? U divided by epsilon and minus U divided by epsilon. Okay. Right? To everybody it is clear why it's like that?
No.
Okay. So I have n particles, but the total quantity of energy that I have in my system is U divided by epsilon. Okay? Let's assume that U divided by epsilon is exactly 1. Exactly 1. How many states do I have in my system? I have to pick one particle. I have n different particles. I have to pick one particle and say you are in the excited state with epsilon. Everybody else is in 0. How many states do I have for this specific situation? N, right? Because I can choose n different particles. I can choose n different particles. Right? So the total number of states is n. The general question is slightly different. Right? I have n particles, and I have to distribute between them. Okay, let's assume I have n particles in the box, and I'm choosing only U divided by epsilon particles that I'm going to excite. How many ways, different ways, do I have to performing this choosing algorithm? N over U over epsilon. Right? This is N over U over epsilon. Okay. So this is a combinatorial problem from the first year. Right? The problem of choosing out of n particles, U divided by epsilon different particles. What do we do from now? Yes, each particle can be, it's a two-state system. Either epsilon or 0. Okay, so the particles that we choose, we excite. The particles that we do not choose, we do not excite, and it has 0 energy. Yes? Can I say it again? Okay. So I have a box. I have a box. And inside this box is n particles, n different particles. And I'm choosing 3 particles out of the box. What is the number of ways to choose 3 particles out of the box that contains n particles? Is n over 3. Is n factorial by 3 factorial n minus 3 factorial. Okay? Now, if I'm choosing not 3 particles, I'm choosing U divided by epsilon particles. Okay, so the only thing that I do, everywhere that is 3 is written over here, I write U divided by epsilon. Okay. So if I simply have 1, okay, if I have 1 particle, okay, so if I'm choosing 1 particle only, so I have n factorial divided by 1 factorial divided by n minus 1 factorial. This is equals exactly n. So, but this is a general equation for K. Okay. This is a choosing problem. If I have n particles and I need to choose out of them K particles, disregarding the order, is just n over K. If you want, I will prove it to you, but a little bit later. Okay. So this is our omega. What do we do? Exactly. And Sterling.
אפשר רק שאלה לפני?
Yes.
מה ההבדל בין הבעיה הזו לבעיה הקודמת? למה עכשיו אפשר להשתמש בצ'וז?
Because it's the same. Beforehand, any particle could obtain the full energy, right? There was no restriction to how many quantums of energy each particle can obtain. Here, each particle is a two-level system. Either it has 0 or it's epsilon. It cannot have 2 epsilons or 3 epsilons. Right? This is why I'm simply choosing. Right? I'm late, I'm sorry. One, I will explain to you, don't worry. N factorial divided by U epsilon factorial. And here we have N minus U divided by epsilon factorial. Okay? I use Sterling approximation. Okay? And it equals to, let me write down the final equation. And it equals to U divided by epsilon minus N, ln of 1 minus U divided by N epsilon, minus U divided by epsilon K bolts, ln of U divided by N epsilon. Alright, so I take this equation and I write that 1 over T equals to ds to du. Okay. And I obtain the equation that is simply U equals to N multiplied by epsilon multiplied by 1 over 1 plus e to the epsilon by k both on T. So what I have done, I have taken this, I've taken the Sterling approximation exactly as I did in the Einstein model, right? And then I have taken the derivative. Okay, so this is again this simple equation that I'm getting. Okay. Now look on this. I have the energy is equal to the number of particles, so this is extensive. This was part of my assumption, multiplied by the energy in the excited state, and some sort of a prefactor. Again, in this prefactor, what appears is e to the power of the energy divided by k Boltzmann. As I said to you, this is going to appear again and again in our class. Now, why this simple example of two-state, and I'm sorry that I'm having even provided here all the details, why it's actually interesting and important.
What is the question again?
Why I have described to you the two-state problem.
Oh, it's funny.
No, it's not. Okay. So when we're dealing with a thermal system, the heat capacity CV du to dt. Okay. So the rate of change of the energy with the temperature is the specific heat capacity. Okay. Now this is something that I can go in the experiment lab and actually measure. I heat the system a little bit, I change the temperature, I measure by how much the temperature have changed, right? And I can look, and I can actually look on the behavior of the specific heat. So this is something, a quantity that is measurable for a real life system. Now, if we have this expression for U, okay. So it's basically d to dt of whatever we have over here, and epsilon multiplied by 1 plus e to the epsilon by k Boltzmann tree. Okay? So we take this derivative. The function of CV as a function of t looks like this. So it starts from 0, it's rising up, it has a maxima, and then it's decaying to 0. Right? So this peak over here, it has a specific name. It's a Schottky hump. Otto Schottky, yes. The engineers probably have heard about Schottky. Okay? So what happens over here? Now, why it's important? So you know how I can observe different behaviors of the system, and I can learn something about what's going on inside. The measurement of the specific heat is a macroscopical measurement. It's a macroscopical measurement. Okay, so, but by looking on the behavior of the specific heat, I can learn something about the microscopical behavior. Right? So what do I have over here? I have a system that has 2 states. Right? It has only 2 states. And I can excite this system. How I excite it? By providing more energy to the system, by basically getting my temperature higher and higher. The particles will prefer to go from the 0 state to the excited state. Okay? So by enlarging the temperature, the heat capacity rises up. So the rate of the increase of the temperature of the energy is rising with temperature. This is fine. Okay? But what's going on for extremely high temperatures?
They're going to the base state.
So all of them, what happens at the high temperatures, all of them are going to be excited, right? If my temperature is very, very high, according to this formula, right? Temperature is extremely large. Temperature is extremely large. U goes simply to what? N multiplied by epsilon divided by 2. Look at this. So e to the some power, when this guy is, when t is large, this is e to the 0th power. So this is simply 1. So this is 1 divided by 1 plus 1. So for high temperatures, u goes to a constant. So if u goes to a constant, the derivative of u with respect to temperature goes to 0. So this is how I can interpret specific peaks or specific maximas when I measure the specific heat. What it means is that I reach a specific energetic level and I cannot go over it. Whatever happens is my particles are excited to the next level, but they are not going to the level that after the excited state. Okay? This is why then I observe a decrease in the specific heat. So each time I see a specific hump, this is what is called Schottky hump, on the CV as a function of T, I know something about the structure or the energetic structure of the microscopical world. Okay? Simple analysis about macroscopical behavior tells us what happens on the microscopical level. We will continue on Tuesday. The quiz, yes, the most important thing. The quiz is next week on Tuesday. It's going to happen during the lecture, so you have something like 45 minutes. It's going to be only one question, and the topics are whatever we have managed to learn up to this class. Right? So all thermodynamics and phase transitions, not including the statistical mechanics that we learned today. That's it.